So we're going to focus on two equations first, and those are these right here. So we have delta G prime naught equals this, and delta G without the prime naught equals this. So there's four terms I'd like to introduce. Delta G prime naught, delta G, K equilibrium, and Q. And so we'll focus on K equilibrium and Q first. So up here we have a reaction. A plus B yields the products C plus D. And an equilibrium constant would be the concentration of the products, C and D, divided by the concentration of the reactants. And that would be at equilibrium. So you dump A and B into a test tube and you just wait for, say, 30 minutes until it's reached equilibrium, and then you find the concentrations of each part at equilibrium. Now Q, which you'll hear called the law of mass action in biochem, it's nearly the same thing. You find the concentration of C, or of products, divided by reactants. But instead of being at equilibrium, it's the concentration right now, before equilibrium has been reached. So you would dump A and B into the test tube, and you'd wait like 30 seconds, or you would just dump it in and find the concentrations right now. And so you don't wait that 30 minutes to find the concentrations at equilibrium. Okay, delta G prime naught is the free energy of a reaction in a test tube. So you do ATP hydrolysis in a test tube, and you get a certain delta G, and that would be a delta G prime naught. But the delta G without the prime naught is what is the free energy you get in the body. And so, because we can't run experiments like in the body, so we can't really find out what the free energy change is in the body, we find out what the free energy change is of a reaction in a test tube, and then we can plug that number in right here, and we can then find what the actual delta G would be. So here's a question. So go ahead and pause the video and read it, and then unpause it. Okay, so the most important terms here are actual free energy and standard free energy. Whenever you see standard, that's what this little circle means, and so we know that standard free energy is negative 30.5. So we could use either one of these equations so far, but they ask us to calculate the actual free energy, so we know we need to use this equation. So we just plug in that negative 30.5 right here, and R is 8.315, so we'd put 8.315 in for there. But note the units here. So I have here, be careful, and we're going to look at the second one. Convert kilojoules in delta G prime naught to joules, because R is given as a joules unit. And so we would have to take this negative 30.5 kilojoules and multiply it by 1,000 to get negative 30,500 joules. Plug that in there. You put in 8.315 joules. For the temperature, we'd take 37 plus 273. And so to find Kelvin, you always add 273. And then you take ln, and then Q, we would just write out a reaction right here. So ATP yields ADP plus PI. So for Q, we would take ADP times PI divided by concentration of ATP. But you have to be careful. You always have to note the units. And so in the problem, we're given the units as millimolar. So we'd have to convert that to molar. So you would take 2.25 times 10 to the negative third, 0.25 times 10 to the negative third, 1.65 times 10 to the negative third. You would just plug all those in and you would get, you now have all the variables and you can solve for delta G. So note the difference between the numbers of the delta G's. So the standard free energy of hydrolysis of ATP, you get negative 30.5 free energy. But in the body, when you do this problem, you get negative 52 kilojoules. So there is a difference between the two. So this is what you get in the test tube, and this is what you get in the body. Delta G's are additive, and so I have a little example right here. ATP, let's say you cleave off a pyrophosphate, so you cleave off 2 phosphates, that will give you a delta G of negative 45.6. So that's how much energy you have to do work after you've done this reaction. And then let's say you take that pyrophosphate and you cleave that in half, you would get negative 19.2. And so if the question was asked, what is the total free energy for these reactions, you would just add these two together. Something to make note of is that whatever is in the products in this first reaction should be a reactant in this second reaction. So if this reaction was flipped and this PP was over on this side as a product, that should be a red flag to us that both of these are in the products. And that would tell us we would need to flip this reaction. And so if this reaction had this PP as a product, they would have given us this delta G as a positive 19.2. We would have needed to flip this reaction, and then we would need to put a negative sign in front of what would have been a positive number. And then you just add them together. If you ever have equilibrium constants, you multiply those. Here's a table that's showing equilibrium constants and their relationship to delta G. And so we see that as we have a higher number in the equilibrium constant, we have more product. As we have a lower number in the equilibrium constant, we have more reactants. So the higher the number, the more products. Well, let's go back and look at this reaction. So if we have a larger number, that means that the number on top is larger. So let's say this is 5 and this is 1. So that means we would have 5, and remember this is product divided by reactant. So we would have 5 products divided by 1 reactant. Therefore, the larger number yields more products. And we also see that as the equilibrium constant gets larger, the delta G gets more negative. As the equilibrium constant gets smaller, sorry, I think I said that wrong. As the equilibrium constant gets larger, delta G gets smaller, and as the equilibrium constant gets smaller, delta G gets larger. So this is less spontaneous, this is more spontaneous. So the larger the equilibrium constant, the more likely the reaction is to proceed to the right. Okay, these are 5 types of reactions in biochemistry. Number 1, you can make or break carbon-carbon bonds. You show that with a heterolytic arrow. And so this is a heterolytic cleavage, a double-sided arrow. Most important type you'll see are going to be decarboxylations. The second type is isomerizations, eliminations. And so that's going to be just a movement of atoms within one molecule. And you can have cis-trans arrangements. You can have double bond movements and eliminations. Third type are free radical reactions, and those are shown with a homolytic arrow, and so you're going to have one electron. Group transfer reactions, so you can transfer a phosphate group, and if you were to do that, the enzyme would be called a kinase, and more specifically it would be of the category of transferase. Acyl transfer, you transfer an acyl group, and that's going to be an example of that is acetyl-CoA. And then oxidation reduction reactions, and carbon can exist in 5 oxidation states, and we'll go through those later in the presentation. This is just showing the relationship between delta G and equilibrium constant. And so if delta G is negative, the reaction is spontaneous and it will proceed forward, and equilibrium constants will be greater than 1. And it's the opposite down here. If delta G is positive, the reaction proceeds in reverse, and your equilibrium constant will be less than 1. So if an equilibrium constant is large, do you have more product or reactant? If it proceeds forward to the right, we're going to have more product. This is showing homolytic cleavage, which is free radical reaction. This is showing a heterolytic cleavage, where you can make or break carbon-carbon bonds. And so we see we can make carbanions, we can make carbocations, we can make hydrides, or we can make protons. These are 3 specific types of reactions we see within the make or break carbon-carbon bonds. You can have an aldol condensation or a Claisen condensation. And these are probably bringing back bad memories of OChem. But here's decarboxylation, and I highlighted this one because you'll see this one a lot. So this is an important one to keep your eye on. And decarboxylation means you're going to lose CO2. This is showing an example of the second type of reaction. This is an isomerization. And so here we're going to flip these 2 groups. We're just going to move atoms within the same molecule, and that's done by an isomerase. This is showing an elimination reaction where we eliminate water. So kick off water as OH and H, and you form a double bond. Here's a free radical reaction. It's just showing you have a single electron with the homolytic arrow. And here's a homolytic cleavage. And you don't need to know these reactions. It's just it's more important to just know this part, the type of reaction. So here's an oxidation reduction reaction. And I have a little mnemonic here just to refresh your memory on how oxidation reduction works. So Leo the lion says grr. Losing electrons is oxidation. Gaining electrons is reduction. So we could look at this reaction and we could predict if the forward reaction is reduction or oxidation. So we're losing electrons, and losing electrons is oxidation. So proceeding to the right, we have oxidation. And if we're oxidizing a molecule, we should see that it gains more oxygen and loses hydrogen. And so we see that we have a double bond right here. And in the reverse reaction, we're gaining electrons. So that is gaining electrons is reduction. So this is a reduction. Anytime we see a reduction, we will expect to see an addition of hydrogen. And so we do see that. And within this category of reactions, you're always going to see, well, you're often going to see a dehydrogenase. This is going to be a really important type of enzyme. And a dehydrogenase, just think about what the name means. So you might be tempted to think removal of water, but that would be a dehydratase. And so this actually looks like hydrogen. And you see it says hydrogen right here. And so it's removing hydrogen. And so as we move in the forward reaction, we remove hydrogen, and whenever we remove hydrogen, electrons follow. This is pyruvate. He's going to be pretty important later on. And so within the oxidation reactions, there's 5 oxidation states of carbon. As we move downward, we become more oxidized, and carbon dioxide is the most oxidized form of carbon. This is showing ATP, and we're just going to look at this little box down here. This is what we're focusing on, the cleavage of ATP. So we're going to cut off a phosphate group, just the terminal phosphate with water. So this is called hydrolysis of ATP, and it gives us a negative 30.5 kilojoules delta G prime naught. But remember, the delta G is negative 52. So this reaction is very spontaneous. So the hydrolysis of ATP is going to proceed very favorably towards products. And there are 4 things that make this reaction occur so favorably. The first is the charge repulsion between all of these phosphates. These are very negatively charged molecules, and the charges are repelling each other. So imagine that you have 3 homophobic football players all crammed into a closet. And once you open that door, they're going to want to get out of there. And it's the same thing with these phosphates. And once you cleave one of these off, it's just going to shoot off like a bullet because of that charge repulsion. And then the second thing is the resonance stabilization of the phosphate that was just kicked off. So it will become stable, and it will lower its energy because of the resonance stabilization. The third is ionization, or the law of mass action. So what does ionization mean? Let's look at the name ion. So an ion has a charge to it. This molecule doesn't have a charge at this point, right here. And so ionization means removal of this proton. And as we remove that, we see that we have a charge right here. And that's going to allow for greater solvation or hydration of the products. So water is going to form little hydrogen bonds with these negative charges. And so you're forming new weak bonds, which would lower the energy state, make it more stable. Another important idea is this law of mass action. And so this is the product. But by removing the hydrogen, we have now changed the product. And Le Chatelier's principle says that a reaction will proceed in the direction of change. So if we were to remove the product right here, the reaction would just have to move to the right favorably. And so if we have OH as a product versus O minus, these are 2 completely different things, different properties. And so it doesn't seem like we're doing much by removing this hydrogen, but by doing so, we actually make a brand new product. See, when we remove this hydrogen, we get a brand new product. And so by removing this hydrogen, we're making the reaction proceed even further towards the right because we're decreasing the product. And so the reaction just keeps moving down because of Le Chatelier's principle, also called law of mass action, or Q. This table is showing that the ATP concentration is kept quite high in relationship to everything else. And that is so that the body has a continual high concentration of ATP so that it can continually proceed to the right. Because as long as we have ATP, it's going to favorably move to the right, and we're going to be able to harness that energy. So the reaction proceeds very easily to the right, so we want to make sure we always have a lot of ATP in the cell. This is showing ATP And here's magnesium. Magnesium always accompanies ATP to dilute the charge. Now we're going to introduce some high energy molecules. And so we see this division right here, -25. Anything above that line is going to be a high energy compound. Anything below that line is going to be a low energy compound. So we have phosphoenol pyruvate, abbreviated PEP. We have 1,3-bis phosphoglycerate, abbreviated 1,3-BPG. We have phosphocreatine and ATP. And then we're going to have glucose 6-phosphate and glycerol phosphate. And so note phosphoenol pyruvate is the highest energy molecule. And so this means when you cut this phosphate off, you're going to have a -61 delta G. It's very energetic. And so just back on figure 1311, we saw that there were 4 things that encourage ATP hydrolysis. And with all the other high energy molecules, we're going to see similar things that encourage their hydrolysis. So with PEP, this is kind of unique in that it's we don't see it in ATP, but it's a tautomerization, which stabilizes the product. 1,3-BPG, we're going to see resonance stabilization of the phosphate, and then ionization and resonance stabilization of the product. And note the delta G on these high energy molecules. -61. 1,3-BPG is going to be -49, so it's about 50. Phosphocreatine, -43. You see resonance stabilization. Here's a thioester. And so I don't think we saw that on this chart. Nope. But a thioester should be on here. So we see ionization, resonance stabilization. So here's the thioester, which means it's a carboxyl group with a sulfur. And this is an ester, which is a carboxyl group with an oxygen. So when you so the thioester has a more negative delta G compared to an ester, and that's because the thioester is not able to have resonance. The ester is able to resonate, which lowers its energy by this much. So when you cut that group off, you only get that much energy. But when you use this molecule as a means of energy, then you get that much. So you get that much more energy because it has not been able to resonate. There's no resonance stabilization. So here we see ATP going to ADP plus PI. It's usually written as a one-step reaction, but it is actually a two-step reaction. So we're going to transfer phosphate to this glutamate, and then that becomes a good leaving group. This is how to make nucleotide triphosphates. We're actually going to use ATP. And so we're going to use ATP, we're going to rip off that phosphate, and there's actually an enzyme that rips that phosphate off. So this is showing this enzyme picks up that phosphate. So that would be the first step in the reaction, right here. You transfer the phosphate from ATP to an enzyme. And so you're left with ADP over here, but here's the phosphate, and you're just going to transfer it right over here to a nucleoside diphosphate, which would become a nucleoside triphosphate. Inorganic polyphosphate is the storage form of phosphate. So this would be analogous to glycogen being the storage form of glucose. This is showing oxidation state of carbon changing. And so this would fall under the category of the fifth type of reaction in biochemistry, redox reactions. So we see here's methane at an 8, and it goes all the way down and down until we get to carbon dioxide, which is the most oxidized form of carbon. So if a reaction changes oxidation state, it will be a redox reaction. So let's look at CO2. Is it a high or low energy molecule? And what about methane? Is that a high or low energy molecule? And so let's look at the next couple slides to answer that question. So I have oil rig and Leo says grr. We just learned that one earlier. This one is oxidation is loss, reduction is gain. Whenever you have electron transfer, energy will be released. That's really important. So lose electrons, oxidation. So if a molecule loses electrons, it's passing those electrons on somewhere, well, there's energy that is released as those electrons are transferred. So oxidation gives off energy. These are showing reduction potentials. Standard means you put prime not in front of it, the E. And so we're going to introduce this new symbol, E. So a reduction potential. So what is reduction? Let's think about that. So first let's look at these half reactions. Note that the electrons are always on the left side. Always on the left side. So the electrons are on the left side. Why? Remember, reduction is gain. And so these are reduction potentials, so we should show a gain of electrons, which would mean we put it on the reactant side. So here's a few items, a few little points about delta E. Delta E is spontaneous when it's a positive number. So this would be very spontaneous. This would be very non-spontaneous. So it's the opposite of delta G. The symbol delta E stands for electron acceptor minus electron donor. The greater the number, the greater the tendency to accept electrons. So if this number is really big, remember it's reduction potential. And let's think about what rig means. Reduction is gain. And so if the reduction potential is really high, that means it wants to gain electrons really badly. So the larger the number, the greater the tendency to accept electrons. So now we're going to talk about NADH. And this is NADH right here. It accepts electrons or donates electrons as a hydride. And so it will always do electron transfers in a chunk, a 2-electron chunk. It is soluble, and enzymes that use NADH are called dehydrogenase. Remember dehydrogen, and so you're removing 2 hydrogens, and electrons will always follow. Next is FAD. Now we're going to kind of contrast NADH with FAD. So the NAD transferred electrons in a chunk and they were soluble. FAD transfers electrons in single electrons, but it's still in 2, so it would transfer 1 electron once, and then it would transfer 1 electron a second time to make 2 electrons having been transferred singly. Note that it is hydrophobic and it will be tightly bound to its enzyme. And that's the end of the show.